In this video, we're going to talk about infinite limits, whatever those are. So for example, let's look at the function 1 over x. You know that that's undefined at 0, and I suspect you know also that it has a vertical asymptote at 0. That's great, but we've been talking about limits, and do limits have anything to do with this function 1 over x at 0 and vertical asymptotes? Well, it turns out limits do have a great deal to do with vertical asymptotes, but it's a different kind of limit. It's an infinite limit. Anyway, let's look at some numbers to get a feel for what's going on. So you remember in the first video where we looked at limits, we were looking at the limit as x approached, I forget what number it was. Let's say it was 3. What we did was we chose some numbers close to 3 and observed what was happening to the function. Well, let's do something similar to that here. Let's take values. We're thinking about this limit of 1 over x as x tends to 0. Let's choose some values of x close to 0 and see what happens. So I decided to go with 1, 0.1, 0.01, and 0.001. Alright, well, you know that 0.1 is the same thing as 1/10. This number, 0.01, is the same thing as 1 over 100. And I don't think I have room to write 1 over 1,000 here, so I'm going to write it up above. Now, I did that to make the calculations a little bit easier. What we're doing here in filling out this row is just taking the reciprocal of the numbers up here. So the reciprocal of 1 is 1. The reciprocal of 1/10 is 10. The reciprocal of 1/100th is 100. And the reciprocal of 1/1000th is 1000. So as x gets closer and closer to 0, you see that what's happening to the y value, the f of x value, is that it's getting much larger. In fact, my guess is that it would not tax your imagination to believe that we could make 1 over x as big as we wanted just by choosing x sufficiently close to 0. For instance, if we chose x to be 1 over 1 million, then f of x would be 1 million. Alright, so this brings us to the definition of an infinite limit. Let f be a function that is defined at every real number in some open interval containing c, except perhaps at c itself. Then the statement, which we will read as the limit of f of x as x tends to c is infinity, or positive infinity if you prefer, means that for every positive number b, and I chose b because it's supposed to stand for big numbers. For every big number b, big positive number b, there is a positive number delta, so that if the distance between x and c is less than delta, but not 0. So in other words, if x is sufficiently close to c, then f of x is bigger than that big number. What it's saying is we can make f of x as large as we want, arbitrarily large even, by choosing x close enough to c. So referring back to the example we just looked at above, we were looking at 1 over x as x approached 0, we would write the limit as x tends to 0 over 1 over x is infinity. That's not quite right. There's a little bit of a problem with this. We let x approach 0 only from the positive side, only from the right side. So this would actually be a limit from the right. What if we wanted to look at the limit from the left? Well, then we would have to consider negative values of x and see what happened to f of x then. Fortunately, I've got a table This looks a lot like the previous table, except all of these numbers are now negative. All those values of x are now negative. So what we're going to get is -1, -10, -100, and -1000. And now it looks like x is getting more and more negative. I'm sorry, f of x is getting more and more negative. We can make x as negative as we want. It doesn't really make sense to say we can make x as big as we want, because x is actually getting smaller. And if I say we can make x as small as we want, well, that is actually true, but it can be a little bit misleading if you're not careful, and maybe you think we're actually getting close to 0 instead of becoming more negative. So I'm just going to say that f of x can be made as negative as we want. As far out to the left side of the number line, or actually, since we're talking about the y-axis, I guess we should say that f of x can be made as far down the y-axis as we like by choosing x sufficiently close to 0. Pardon me. So now we have another definition. Let f be a function that is defined at every real number in some interval c containing c except perhaps at c itself. Then the statement, which we will read as the limit as x tends to c of f of x equals -infinity, means that for every negative number n, so I'm thinking of n as a very negative number, there is a positive number delta, so that if x is closer to c than delta, but not actually equal to c, then f of x can be made less than, n. And by less than, I mean more negative than, farther down the y-axis. And so referring to the above example, we would say that the limit as x tends to 0 from the left of 1 over x is -infinity. And you remember what the graph of 1 over x looks like near the origin. It looks kind of like this. By choosing x is closer and closer to 0, the y values get larger if we're going from the right side, and if we're going from the left side, by choosing x is closer and closer to 0, the y's become more negative. So the limit from the right is positive infinity, the limit from the left is negative infinity. So what would we say about the limit as x tends to 0 of 1 over x? Well, from the right we got positive infinity, from the left we got negative infinity. Those are two different limits. The limits are not equal. So the limit of 1 over x as x tends to 0 does not exist. A second observation I want to make is that this function 1 over x has a vertical asymptote at 0. So vertical asymptotes are all tied up very closely with infinite limits. In fact, here's a note that connects the two. The function f has a vertical asymptote at c if any of the following are true. If the limit as x approaches c of f of x is either infinity or negative infinity. If the limit from the right or from the left is positive infinity, or if the limit from the right or the left is negative infinity, then there is a vertical asymptote. If any of those occur, there is going to be a vertical asymptote. Furthermore, if there is a vertical asymptote, then at least one of those 6 things has to be true. Now, let's also link this back to some things that we've already said. You remember when we talked about rational functions, we talked about removable discontinuities and non-removable discontinuities. And we're dealing with rational functions. The non-removable discontinuities were always vertical asymptotes. Well, this kind of ties in the idea of vertical asymptotes. and expands the idea a little bit to things that don't have to be made up of just a polynomial divided by another polynomial. If f and g are two functions which are both continuous on some open interval containing c, so that f of c is 0 and f of c is not 0 and g of c is 0, then the function f of x defined by f of x divided by g of x has a vertical asymptote at c. So what this is saying is that anytime you have a 0 in the numerator, if there's a value of x that makes the denominator 0 but makes the numerator non-zero, and again dealing with two functions that are continuous near that value of x, you're going to have a vertical asymptote. And linking that fact that we just looked at back to limits, we now know how to figure out when a function has a vertical asymptote. Well, if a function has a vertical asymptote, that means the limit from the right, in the case where we're dealing with continuous functions, the limit from the right is going to be either positive infinity or negative infinity, and the limit from the left is going to be either positive infinity or negative infinity. So, can you find all vertical asymptotes of these functions? In number 1, you've got y equals x squared minus 25 over x squared minus 5x. Well, really what I'm asking you to do is find all the non-removable discontinuities. So let's factor the denominator and the numerator. In the numerator, you've got a difference of two squares, so that will factor into x minus 5 times x plus 5, and in the denominator, you have a common factor of x. The denominator factors into x and x minus 5. So there are discontinuities at x equals 0 and x equals 5. The vertical asymptotes are going to be the non-removable discontinuities. Well, the 5 is going to be removable, so x equals 0 is the vertical asymptote. Alright, and now let's look at number 2. You've got x over the sine of x. So when is the sine of x equal to 0? Well, the sine of x is equal to 0 if x is some integer multiple of pi, so some integer times pi. And I'm going to use an abbreviation I haven't used yet. Mathematicians often use this strange-looking capital Z to represent the integers, and this is saying that k is an element of the integers, or k is an integer. So things like 3 pi, 7 pi, 0 pi, negative 4 pi, those make the sine of x 0. So the sine of x is going... The denominator here is going to be 0 every time x is an integer multiple of pi. And for the most part, that's going to make the numerator non-zero. So that means we're talking about vertical asymptotes. The only value we have to worry about is x equals 0. If x equals 0, the numerator is 0 and the denominator is 0. But so that means, well, what does that mean? Well, in this case, do we have a vertical asymptote? Do we have an infinite limit? Well, I hope you remember what the limit of sine of x over x is, the reciprocal of sine x over x. If you look at the reciprocal of this function and take the limit as x tends to 0, you're going to get 1. Well, if you take the reciprocal of the function, the answer is going to be the reciprocal of the limit. So the limit is the reciprocal of 1, which is 1. You do not have an infinite limit at 0, so you don't have a vertical asymptote at 0. So I need to add the restriction that k cannot be 0.